Hi everyone, I'm Lola. First of all, I'm from Spain, so I have a funny accent. If you don't understand me at any point of the presentation, please let me know. However, no one let me know anytime, but it's fine. I'm an Instagram software engineer on the core client performance team. For a little bit of context, what we do, let me tell you our three main high-level goals. Those are 0 wasted bytes over network, 0 wasted bytes on disk, and content loads instantly. But first, let me take a step back on why I'm here talking about effective data prefetching on background. 2016, as many of you may know, was a great year for Instagram. We launched a lot of features: stories, live, save, collections. Moreover, recently, we just announced 800 million monthly active users. So we ask ourselves, how can we keep improving? How can we make sure that everyone that wants to access our app can go into Instagram whenever they want to? To answer this, we went into various research trips to Indonesia, India, Philippines, Brazil. I actually went myself into Indonesia around a month ago, and we did a lot of data analysis as well. What we discovered is that what it's really preventing users from accessing Instagram is the network availability and the user's data plan. Therefore, effective data prefetching on background is a step taken towards breaking the dependency of the app usability in between these two factors. Network availability around the world, as many of you may know, is a real challenge. Michael, our data scientist, put together this graph. What this represents is the network speed that the user is in when they are using Instagram. This is pretty cool. Let me tell you about how we build this. We logged the network bandwidth estimation on every image and video fetch. Then we computed the average and sliced it by country. The numbers go from somewhere around 4.7 megabytes per second in regions like Canada, that is darker. And then in emerging markets, we have something around 1.44 megabytes per second in Indonesia, or 1.2 for India. What is exactly this telling us? If you want to build a media app, and then you expect to download on real time the images and videos as users are scrolling on your app, you're not going to be able to with this network availability, especially in the lighter green areas. If you want to build a fast photo app in India, where the round-trip time can take up to 2 seconds, you're going to have to come up with different strategies than fetching media on real time. We need to react to the different network availabilities that the world offers us. Why is this an error? How do users feel about this? What will happen when the user goes into your app into a white screen like this? With a screen like this, there is no clean code and no cool features, because the users will background the app and switch to a different one that could offer offline content. What about when we are in one of those light green areas where the network speed is not fast enough? We are going to show the users a bunch of loading spinners. Yeah, that's going to be better than a gray box. And that can keep the user engaged for a couple more seconds. But eventually, the user will lose the patience and abandon the app. I'll tell you something. Humans, we are more and more losing patience with technology. When we unlock our screen and start browsing apps, if something doesn't load, we abandon. We switch to a different one. Our goal is to make the user perceive no network connection as if they would be actually online. We want the app to run smoothly in all these cases. All right. Now I've talked about the problem that we encounter. Because we like to do simple things first on Instagram and Facebook, we first lay down all the use cases that we wanted to solve. Now I'm going to talk about the strategies that we came up to solve all these problems. First, for the rest of the talk, I'm going to focus on the next 5 slides about how we worked on unlocking this content delivery. This is the ability of delivering content from the disk as it would be coming from network. This is not only the image and video cache. For this, you'll also need to have a network cache. This will unlock the offline experience, or what we call offline mode. And second, I'm going to talk about how we built a background prefetching framework. This one will then be populating this disk store that we are going to get the content from. Because when you're doing background prefetching, you need to put your data somewhere. And how many people in here do background prefetching? All right, we have some people in the room. I'm going to show here what is the experience after building the unlocking, delivering content from disk. And I'm going to show you the user experience of the before and after. So to your right, you're going to have the happy case, where we already built this infrastructure. And to the left, the sad case, the before offline experience. This might pitch and sell to you, because I'm going to show you the difference in between these two cases. So imagine that the user goes ahead and goes into airplane mode or a region that doesn't have good connection. They start browsing the app. And before, we were able to show the first page of the timeline with a very base cache. But eventually, the user, after reaching the bottom of the page on the left, they were not able to keep scrolling down or keep engaging with the app. Moreover, we were able, through a pending action store, unlocking the possibility of commenting, liking, and saving media on the app, even though users could not have internet connection. Now the users can also visit their closest friends and family profiles, the ones that they visit often, so it's safe on the cache. They can follow and unfollow. They can also explore new content, even though they are offline. The perception of the app speed is a whole new world. They can review their latest activity or the activity of their closest friends. And last, they are able to review their profile, their latest photos and videos that they posted. As we can see, to the right, we have the case where the app just simply works. We are able to maintain the user engaged and be able to offer them whatever they are looking for. We came up with a series of principles for this offline case that summarize all that we learned through the user experience, user research, and the data analytics. The first one, offline is a status, it's not an error. An error is defined by something unexpected that happened that will make the user leave your app. So we don't want to be in that case anymore. Second, the offline experience is seamless. How cool would it be that users are using and browsing your app? They might get into the subway and they might have lost connection. And they just keep browsing and they don't even notice that they lost the connection. And last, build trust through clear communication. We believe on telling the users everything that we are doing under the covers, so they feel that they are in control of their offline experience or the slow connection experience. All right. Now let's get a little bit into details. The architecture on how we build the response store. Again, for time constraints, I'm not going to get into details on how we build our image and video cache that was there a long time ago. But for the offline and background prefetching, we build the network response cache. This gets populated when the user is using the app and later on with the background prefetching framework. This is how it works. So the user accesses Instagram and the UI screen fire a request task to the device network layer. This device network layer is a component that is on our network stack. It's just one more layer. This one will be in charge of taking this request task and will build the HTTP request object. This one will be handled by the device network engine. We are still on the device. This one is the one in charge of communicating with the server, sending that app, and then getting the HTTP response. Our device network engine is capable of receiving this response asynchronously and deliver the callbacks by batches. So the device network layer will asynchronously receive these batches. What it will do is asynchronously and in a compressed way for efficiency, will write this HTTP response into what we call the device response store. And then at the same time, it will strongly type the response and deliver it back to the UI, as if nothing happens. So when do we use this? So imagine the sporadic network connection case. The UI screen fires again the network request task, and it associates a cache key. It will be sent to the device network layer again, and same story, HTTP request to the network engine. This one now is not going to be capable to communicating with the server at all or fast enough. So then it will deliver an error or a timeout. The device network layer will react for this circumstance in a way that it will read the cache HTTP response from the device response store. For that, it will use the cache key. And this was an interesting part when we implemented this, because we open up the API in a way that the engineers, product engineers, define the cache key, because they will be in charge of selecting a cache key that represents a unique HTTP request. So this takes into account things like pagination. This one then will build the HTTP, the type response, and send it back to the UI screen. So again, as I said, we are delivering content from disk as if it's coming from network. So after building this offline experience, we asked ourselves, is this really useful? So we went ahead and we looked at the metrics on how users reacted to this new mode. We saw improvements on user engagement metrics, especially on emerging markets. So even though seeing the content that you previously downloaded when you were using the app was way better than seeing gray boxes and loading spinners, we asked ourselves, what if we can show the user content that they have not seen before? After all, when you unlock an app, if you just see the same photo that you saw from your friend, you're like, this is all. And then you background the app again, right? So what if when you go into Instagram, even though you're getting into the subway, you can see new content that you haven't seen? Moreover, as I said, one of the problems was also the user's data plan. What if we can take advantage of those situations when you are on free connections and download that content ahead of time so you don't have to download it when you are on cellular connection. So these are the two main drivers for background prefetching. Basically, what we want is to increase the app efficiency and at the same time, increase the value for the user. But we didn't build a rocket to cross the street. We first built a prototype. And this is funny because when I started my career, I hated prototypes. I like to build everything super beautiful and fancy. So it took me a while to digest something like this. But we built a small prototype, a proof of concept. This is very simple. What we first built is that our three main features on App Startup, they will just register 3 runnables. Each of these will prefetch up to 10 medias each into a simple connection or list. As we see, we will call register job, which is a runnable that will download 10 medias. When the app got backgrounded, so just when the user clicked the home button, we will check if we were under Wi-Fi connection. And if and only if, we will just iterate through this list of runnables and just run it on a serial fashion way. Very simple, huh? So now I'm going to ask you, do you think that this provided any value to us? Quite a few. The first one, it allows us to start iterating on what kind of media do we want to prefetch for users. Shall we prefetch 5 stories or 10 stories? 3 or 2? We could start A/B testing on this type of media prefetch. Second, we could observe how delivering unseen content would actually impact user metrics. Because sometimes you think that you're building a feature that is super useful to your user base, but then you launch it and nobody's using it. So we wanted to make sure that we were right. And third, it was super useful for stability. This allows us through A/B testing to benchmark the final framework against this simple thing. This simple thing should definitely perform worse than the finalized framework. And if we were doing things right, we should only be getting better with the finalized framework with this as a baseline. The reality is that apps are very complex, and so are users. So kind of bad news. And this is not going to get better. Only on our main page of Instagram, we see a lot of things that we could be prefetching. Photos on the timeline, new content to discover, messages, notifications, your latest photos or videos in your profile. So we needed a way to be able to scale and apply some control logic in here. Do you imagine every team prefetching everything that they wanted? So we decided, when we were all sitting in a room together, to design a framework that it was centralized, because we wanted to apply some rules. The reasoning is that we wanted to build a framework that it was flexible enough to adapt to the different use cases. Because you might use the stories, but I might not use them. So in those different cases, we needed a framework that is adaptable enough. Moreover, we wanted to apply some logic and rules on top of a simple job scheduling logic. These are, the first of all, is the Wi-Fi connection. I think I said it around 1,000 times, and I'm never going to say it enough. We are very careful about what kind of connection we are in when we are downloading data, and we want this to be a meter for the users. The second one is job cancellation. Imagine that you kick off your background prefetching work. What happens if the user foregrounds your app? You're going to create network congestion. So you need to prevent that. So imagine that the user just received a notification about a friend that just liked that photo. And he's just trying to see that photo that his friends liked. But you're doing still all your background prefetching. What you want is to be able to cancel all that job that does no longer matter to the user and start doing the things that really matter to them. The third one is batching requests. When you batch requests, you reduce network overhead. And the last one is metrics, collecting metrics at a framework level. It's very important that you have the proper metrics in place if you're going to do background prefetching. Who was, again, the people that were doing background prefetching in here? Can you raise your hand? All right. We have some people in the room. Prefetching is a trade-off, as everything in software engineering, right? So what you want is to properly measure the benefits versus the cost. So what we wanted to have in place is the proper metrics about data usage and time spent, and also the cache efficiency metric that will allow you to measure the wasted bytes over network and on disk. I'm going to explain about the workflow of the components on the Instagram app for the background prefetching framework. First of all, the user foregrounds the app. So it goes into Instagram. What we do is that we instantiate what we call the background Wi-Fi prefetcher scheduler. This little guy is going to be in charge of collecting what kind of runnables or what kind of work do we want to run on the background prefetching job. So what kind of things do we want to prefetch, basically? So it will ask the main features or prefetcher utilities, hey, you, what do you want to prefetch? So these prefetcher utilities will register their work into the Wi-Fi prefetcher scheduler. After that, this one will register itself as a listener in the delayed background detector. For context, on Instagram, we have a delayed background detector that will notify our components when the app gets backgrounded so we can do low priority work. So the app gets backgrounded and our scheduler gets notified. Now what is going to happen is that this component is in charge of building a job request. It's going to be responsible for scheduling the background prefetching job. This is a general job that runs one time in between sessions and will run the data that the prefetcher utilities requested to. So it will call our Instagram job scheduler that I'll get into details in a few minutes. And it will pass the job info, the job parameters. So we need two conditions to be met for our background job to be kicked off. These two conditions go by order. The first one is latency, and the second one is network connection. This means that for simplicity, let's say that my latency is 10 minutes. So when the background Wi-Fi prefetcher scheduler calls a scheduled job with 10 minutes of latency, 10 minutes later, the second condition gets evaluated, that is the network connection. Can you guess what network connection we require? Wi-Fi. Thank you. So if you're on Wi-Fi, the background prefetching job will get kicked off. By the way, if in the meantime, the user went back to Instagram, we cancel the job. And we are using job scheduler, the Instagram version, also for efficiency. So we can take into account the device context, battery, and other type of relevant information. So, okay, so imagine that we set 10 minutes. So 10 minutes later, we evaluate Wi-Fi connection. If we are on Wi-Fi connection, we kick off the job. If not, we wait until we are on Wi-Fi connection. And as soon as that moment happens, the background service starts. And we start doing all the prefetching that the features utilities have requested. The background service will keep track of each of those. And after all single one of them are done, we will notify the OS. This is very important because we want to release our resources and we want Android to release and kill our process, so we release the no longer need the resources on memory. All right, I promised that I would talk a little bit about Instagram Job Scheduler. Who in here is using Android Job Scheduler? All right, some people. So the story goes this way. When I was looking on how to implement this, I started looking into the Android Job Scheduler. This framework, for those people who don't use it at all, is a job scheduling framework that has a very, very good API. It has a bad. It only works for Lollipop and above. So then I asked myself, well, maybe Lollipop 2014, we're not going to have that many users under Lollipop. Let me just check how many users do we have under Lollipop devices, like running under Lollipop, under devices. I was not lucky. So then I decided to explore other libraries, which I'll mention in the next slide. And even though all of them were great, it quite didn't work for us. So I built a custom solution using Alarm Manager and Broadcast Receiver. The options that we observed that was out there were, these are the main options. Of course, we also had the Facebook internal one. The main options was Firebase Job Dispatcher, Evernote's library, and Doist library. We couldn't use Firebase Job Dispatcher. That is very up to date, and Google is definitely collaborating with them by Google. But it pulls in the Google Play Services dependency because it uses the GCM. At Instagram, we want to keep our first-in-class position in terms of APK size, and we measure what was the APK increase after pulling this in, and we decided to not to do it. Evernote's library is great, but they have a different API, and they seem to have some stability issues as well. But when I was looking for other solutions, and Doist library was not actively maintained. So now let me tell you about how we schedule the background job to be run. This happened, to refresh your memory, when we background the app, right? That Wi-Fi Prefetcher scheduler. So it's very simple. It just needs to build the job request and pass it into the Instagram job scheduler. So this is the code that we have today in our class. First, through the builder, and the job ID, we build this job request. It's very similar to the job scheduler API. We then set the required network type and the latency. By the way, I kind of lied when I said that we choose 10 minutes. We obviously try to choose a dynamic latency. What we did in our first version, we are currently experimenting with different latencies, was to try to predict, or that this is our goal, we try to predict when is going to be the next time that you access Instagram. So we prefetch right before. The more fresh the content is, the better. What we did in our first version was computing the average time in between those times when you access Instagram. And then we remove outliers using the standard deviation. For those times, when you go to sleep and then you haven't accessed the app in 10, 12 hours, that for some people might be normal, but for me definitely is not. So it's an outlier. And then we prefetch on a P75 of your average, so 75% of that time. That being said, this is how we build the job request that we pass into the job scheduler. So now let's get into details a little bit on our compatible version of the job scheduler. I'm gonna go through these a little bit faster, given that some people in here, most of you seem to not be that familiar with the job scheduler API. When we go to schedule the job, if we require some latency, we create an alarm for this. Again, I'm explaining a little bit about the compatible solution that we built. So this is only for devices Lollipop and under Lollipop. So we build the alarm for the given latency and the class pass in. So we use the alarm manager for this. And after that gets kicked off and the alarms goes up, we will check the connection type. If we are not under Wi-Fi connection or the connection required, we then will enable a broadcast receiver. For this, we build an Instagram job scheduler store. This one takes care of keeping track of those classes that could be waiting for a network connection. That way we'll only have one broadcast receiver. We are the performance team, so we are very picky about our performance of our app. So we want to minimize at any cost the battery usage and memory usage. After that, we will enable it if it was not enabled before by any of the other components and pass it into our component, into our broadcast receiver manager. Metrics. This is my favorite part, to be honest. Why am I talking about metrics? It's because I strongly encourage you that if you want to build a scalable and efficient background prefetching framework, you first think about putting the metrics in place. It's very important that you are able to evaluate the cost. So not only looking at the benefit. As a pre-step, I need to talk about something that we had before that has helped us a lot. We tag every network request on Instagram with something that we call a request policy. This tells us if a request is an image, video, API, analytics. And also it will tell us if a request is an on-screen or a prefetch request. This is a snapshot of that behavior that I said for the on-screen or off-screen. Off-screen will be prefetch. And for definition, we consider a prefetch request all kind of request that has greater than 1% chance of not being seen by the user. With this, we build the cache efficiency logger. This cache efficiency logger is a great metric and measurement to observe how many bytes are you wasting over network. It will look at all those bytes that you put in your cache that was unused by the users. So it computes different cache statistics. So if an item was put into the cache and it was a prefetch item and you never use it, you basically wasted those bytes over network and on disk. We wanted this system to be, first of all, scalable. We have different cache implementations. So our image cache and our network cache, they do not look the same. They do not have the same API. Same for our image. So we wanted to be able to align all these three. We wanted our component to be scalable enough to adapt to the different cache instances that we had. We wanted also to be tolerant. Again, I/O operations, a lot of exceptions, right? We needed to be able to adapt to those files that were also corrupted and react appropriately. Moreover, we wanted this to be reliable. We didn't want to just collect data in memory and report it, and it was too messy. So we decided to persist the data on disk. And last, we wanted it to be efficient. Reads and writes on the cache happen all the time. And we wanted to introduce zero latency overhead on those reads and writes because the user might be waiting for any of those items. So what we did is to offload this work into a background thread and had an in-memory buffer. So something like this. We had a file thread handler that when we detected a new event, if we were over the buffer side, we will perform the write into a file. Not in the same thread, not in the color thread. This is very important. Also, I'm going to do a quick mention to yesterday's talk about SQL, the resurgence of SQL, where they also mentioned about performance trade-off of SQL versus flat file. I'm actually currently A/B testing flat file versus SQLite, but we are going to go with the flat file because for our use case, where we basically just add items and append items to the end and report and scan when we want to read, is way more efficient. The reason is because we don't have to have a single thread dedicated for this. We only use a low priority background thread to do all this work. And it actually causes 0 performance overhead on users. Quick mention that we built our data usage tracker as a network layer. So it was just a proxy observing all the requests that were going in and out. This way we could also have how much bytes do we use on Wi-Fi or on cellular, and also slice this data by image or video thanks to our request tagging. Other benefits is battery usage. Prefetching as itself is a network performance improvement mechanism. When you are bundling future requests together, you reduce that network overhead and reduce the risk of waking up the cellular radio all the time that comes with the battery trade-off. Other risk, global CPU regression. This is kind of my worst nightmare right now, if I'm honest. Think about this. Imagine that your app makes a call to the timeline API once per session or twice per session. But now, in between sessions, you're going to make another call. You're increasing that load on that endpoint by 50% or 100% even. You might be doubling up this server load on that API endpoint. So that's something that you need to watch for. As a quick mention, we opened up a new different endpoint on Instagram for main feed that just retrieved the 20 newest media to avoid that case. So from prototype to ship, we took care that efficiency was there in place all the time. And our main key takeaways are that background prefetching definitely increases the app perceive. We saw this on the way that users started using the app after launching our framework. A centralized framework will help scaling with a code base or an app that has like multiple features. And last, metrics are key to evaluate the trade-offs. That's it. Sorry very much. I ran over the question time, but the lady on the back is yelling at me. So if you have any other question, please come by our booth and ask anything that you want to ask us. Sorry again for running over.